You know, when you think about discovering the secrets of the universe, you probably picture these giant, massive machines, right? Billion-dollar space telescopes or particle accelerators that are, 27 kilometers long? But what if I told you the biggest discovery of our lifetime, actual proof of a fifth dimension, wasn't hiding out in the cosmos, but right here on Earth, on a tiny little lab bench in France?
Yeah, that's the incredible, almost unbelievable question we're going to dig into today. This is one of those stories that doesn't start with some huge explosion, but with a quiet, tiny little mystery that was hiding in plain sight.
So our story kicks off in Grenoble, France, at a place called the Laue-Langevin Institute. This is where a super high-precision experiment accidentally stumbled onto something that, well, standard physics just can't seem to explain.
The experiment itself is called qBOUNCE, and what they do is pretty cool. They take these ultra-cold neutrons and just drop them onto a perfectly smooth mirror. Now, you'd think they would just bounce, right? But this is the quantum world, so things get really weird. The neutrons don't bounce continuously. Instead, they hover at these very specific, distinct energy levels. It's almost like they're levitating on a set of invisible stairs.
And for years, this experiment went off without a hitch. Everything worked perfectly. But back in 2014, the researchers noticed something odd. When they measured the neutron's jump from one of these quantum stairs to another, the result was just slightly off from what Newton's law of gravity said it should be. It was tiny for sure, but it was also very, very persistent. It just wouldn't go away.
So what do you do when you get a number that just doesn't fit? Well, in physics, sometimes you have to add a little mathematical patch to make the equations work out. You can think of it like a fudge factor. In this case, they called it the Robin parameter, or lambda. They just plugged in this tiny value, 2.73, and poof, the math worked. For most people, this was just some measurement quirk, a bit of background noise. But for one theorist, it wasn't noise at all. It was a signal.
And this brings us to a really radical new explanation. What if that tiny little anomaly wasn't an error? What if it was the first faint whisper of an entire hidden dimension? This is where the oscillating brane theory comes in. The idea is that our entire three-dimensional universe is just a membrane. They call it a brane for short. And this brane is vibrating inside a much larger, five-dimensional space. And according to this theory, gravity isn't trapped in our little brain with us. It can actually leak out into that fifth dimension. Okay, and here is where this whole thing goes from a vague, kind of sci-fi concept to real, testable science. The theory, which is actually based on cosmological data about dark energy, makes a very, very specific prediction. It calculates the thickness of this fifth dimension to be precisely 0.2 micrometers. That's not a guess, that's a hard number you can actually go out and look for. Right, so how on earth do you connect a huge cosmic theory about a fifth dimension to a tiny little anomaly on a lab bench? Well, the answer, as it so often is in physics, is hiding in the math. All right, don't let this equation scare you. We're going to break it down. It basically describes the extra little gravitational pull that a fifth dimension would create. Most of these symbols are just standard things, like the mass of the mirror and the gravitational constant. But the real secret, the part that changes everything, is this little bit right at the end, the exponential term e to the power of minus z over L. That is the absolute key to this whole mystery. So let's plug in the numbers from how the qBOUNCE experiment works right now. Z, that's the distance of the neutron from the mirror, is about 1 micrometer. L, that's the predicted thickness of the fifth dimension, is 0.2 micrometers, so that key term becomes e to the minus 5. And e to the minus 5 is a crazy small number. It's about 0.0067. This means the effect of the fifth dimension is being squashed, suppressed, by more than 99%. It's almost completely hidden, which is exactly why they only see that tiny little anomaly of 2.73. Okay, so explaining the past is one thing. But a real scientific theory has to predict the future. And this is where this whole idea makes a bold, dramatic, and completely testable claim.
So get this. The team in Grenoble, they're upgrading their experiment as we speak. And their goal? To get 5 times closer to that mirror, to get their resolution down to that critical distance of 0.2 micrometers. So what does the math predict is going to happen then?
So let's plug in the new numbers. Z, the distance, is now 0.2 micrometers. And L, the predicted thickness, is also 0.2. So our key term becomes e to the power of minus 1. That is a huge difference from before. The number just jumps from a tiny 0.0067 all the way up to 0.37. The suppression is just gone. The hidden signal from the fifth dimension is suddenly totally unleashed. And here is the absolute kicker, the stunning result. The theory doesn't just predict the anomaly will get a little bigger, it predicts the signal will explode by a factor of 55.
I mean, just look at this comparison. On the left, that's the tiny anomaly they see today, that little value of 2.73. On the right, that's the predicted value when the experiment gets down to 0.2 micrometers, a massive explosive jump to around 149. This isn't some subtle little shift, it's a monumental leap. It's either going to be there or it isn't. No ambiguity.
So, the crucial point is, what would this actually mean? I mean, a fifth dimension is super cool, sure, but discovering it could fundamentally change technology by giving us a way to hack one of the most stubborn rules in all of quantum physics.
You know that huge roadblock for quantum computing? It's called Heisenberg's uncertainty principle, and it basically says you can't observe a quantum state without totally destroying it. It's a fundamental problem. But this theory, it offers a secret passage. Since gravity leaks into the fifth dimension, you could potentially measure the gravitational shadow of a qubit from that other dimension. You could literally read its information without ever touching it with a photon, completely bypassing the very act of observation that causes it to collapse. It's a total game changer.
This is what's so exciting about all this. It isn't just philosophy. The theorist behind this has laid down a clear, confident challenge. The prediction is on the table. It is binary. Test it. It will either jump by a factor of 55 or it won't. If it doesn't, hey, the theory's dead. But if it does?
And that's where we are right now. The experiment is being upgraded. The test is going to happen, and the result will be a simple yes or no. If it fails, well, it was a beautiful idea. But if they find that signal amplified 55 times, it will mean we've been living right alongside a hidden dimension this whole time, and it will force us all to ask a really profound question. What else, what other fundamental secrets about our own reality are hiding right in front of our eyes, just waiting for the right experiment to come along and reveal them?